In some earlier videos, we talked about the idea of a truth table. And so let's say we want to see the truth table for what's called a logical AND, which you see in programming, you see it in logic and that type of thing. So it might give you something like this. We'll say, okay, we have A, we have B, and then we have A and B. And the table would say, okay, well, A could be true and B could be true, and when that's the case, A and B has a value of true. And then we say, well, A could be true and B could be false, and A and B then is false. And then we have false and true and false, and these are both also false. So we see here, we have 4 rows in this table. But this is the 2-value case. What if we had, A and B and C, or A and B and C and D, or A and B and C and D and E, and so forth? How do we know in advance how many rows our table would be? Well, it turns out there's an area of mathematics that deals with that, and it's called combinatorics. In reality, go back and look at this example. This wasn't that difficult to do, but even if we got up to like the 5th, or the version where we have A and B and C and D and E, this table would have 32 rows. That is, it would have 32 different arrangements of these true and false, and that would be painful to do by hand. In many real-world situations that use combinatorics could have millions or billions or even numbers so large, I don't even know the names for them. So we need some way of just calculating the quantity of things, and that's where combinatorics comes in. It's the mathematics of counting. So in the beginning, 2 of the easiest things we can do are use what's called the multiplication principle or the addition principle. And we'll see the addition principle here in a moment. But let's look at this definition first. Multiplication principle says that if we had a sequence of events, E1, E2, ... with possible outcomes, N1, N2, ... then the number of distinct sequences is N1 times N2 times N3, and so forth. So what would be an example of something like that? Well, we can look back at what we had here, and how do I know this? Well, how many different values can A take? Well, true or false, so we had 2 of those, and B could take on 2 values, so 2 times 2 was equal to 4. That's how I got the 4. And that means if we'd had A, B, and C, we'd have 2 cubed equals 8, A, B, C, and D, that'd be 2 to the 4th equals 16, and finally A, B, C, D, and E would be 2 to the 5th, which is 32 different arrangements. Now notice I'm using the word arrangement as opposed to combinations. In everyday English, I might choose to call those combinations of true and falses. But it turns out that in combinatorics, the word combination or combinations has a specific mathematical meaning, which doesn't always match up with the general English usage. So that's why I'm trying to use alternative words like arrangements or orderings or something like that. Although sometimes I still don't know what to use in place of combined or substitutions or combinations or whatever. Okay? So what would be another example? Well, what if we said that I had 3 t-shirts and I have 4 pairs of shorts, and I want to know how many different ways can I combine these? How many different outfits can I put together? So according to this formula that says I have 3 possibilities, that's the N1 here, 3 different t-shirts. And when I'm thinking about these types of problems in my head, I'm often using this phrase, for each. So I have these 3 t-shirts, and for each of those t-shirts, I can wear one of the 4 pairs of shorts. So 3 times 4 is equal to 12. Now, one of the things that really helps when thinking about these types of problems, when it's a small number of things like this, is to create what's called a decision tree. So here we could say, okay, I could have t-shirt 1, t-shirt 2, or t-shirt 3. And we can see that if I choose t-shirt 1, I have 4 different pairs of shorts I could wear. S1, S2, S3, S4. If I choose t-shirt 2, I have 4 different pairs of shorts. T-shirt 3, 4 different pairs of shorts. So I could have, t-shirt 1, shorts 1, t-shirt 1, shorts 2, and so forth. And we see this is 1, 2, 3, 4. This will be 4, this will be 4. So 3 times the 4 is my 12. But this allows me to visualize it and understand what's happening there. Sometimes, though, we have a set of things and we're exhausting things from that set, and so maybe we don't allow repeats of certain things either. So what if, for example, I had some food at home and I have some eggs, I have pancake mix, and bread for toast. But I only have enough of each for one day's worth of breakfast. So how many different orderings are there for what I could eat? Well, you can see here, if I draw the tree, I could have eggs one day, followed by maybe pancakes the next day, followed by toast the third day. But I have eggs, and then maybe instead of pancakes, I choose toast, which leaves pancakes for the next day. But what if for the first day I wanted pancakes? That means I could either choose eggs or toast for the second day. And if I choose pancakes followed by eggs, then all I have left is toast for the third day. This would be eggs. And finally, I could choose toast the first day, eggs or pancakes, and then pancakes here and eggs here. Okay? So how does that work? Well, you can see here this would be eggs, pancakes, toast, eggs, toast, pancakes, and so forth. So it's 1, 2, 3, 4, 5, 6. That's 3 possibilities for the first thing, followed by only 2 possibilities for the second thing, followed by 1 possibility for the third thing, which is 6 different arrangements or orderings, and this happens to be 3 factorial. So that's how I would answer that question. Let's look at a couple more examples. Or actually, let's look at the addition principle. So the addition principle says that if I have these disjoint events, E1, E2, ... with possible outcomes N1, N2, then the combined number of outcomes is N1 plus N2 plus ... I no longer am thinking for each, because I'm not saying choose something and then for each of the possible values choose something else. I'm really sort of combining things. So what if I had to choose between wearing 10 different t-shirts, or I had 2 suits, but they're disjoint, so I would never combine these. I'm either wearing a t-shirt or I'm wearing a suit. And how many different things can I choose from on a particular day? Well, I have my 10 plus 2 equals 12 different outfits here. Okay? So now let's see one more example, or 2 examples actually, based upon the same basic idea. So let's say I go to a website and they tell me to choose a password. And so they say your password has to be 8 characters. And your choice of characters are the 26 uppercase characters. That's A, B, C, like this, ... The 26 lowercase characters. That's little a, little b, little c, ... And the 10-digit characters. 0, 1, 2, ... So what do we have here? Well, 26 and 26 is 52, plus 10 will be 62. So I have 62 different characters to choose from for the first character. For each of those, I have 62 for the second character. For each of those, I have 62 for the third character, and so forth. And so what I have here is 62 to the 8th power, because there would be 8 62s here multiplied together. This is a monstrously huge number. Okay, 62 squared is 3,844. And so 62 to the 8th power is just really big, okay? So this was only the multiplication principle. But what if what they said was this? My password still had to be one of these 62 characters, but now it had to be 5 to 8 characters in length. Okay? So if I were to choose a 5-character password, then I have 62 to the 5th different arrangements, but I also could have 6 of these, right? So that leads to this, 7. And if I were to choose the 8-character version, or excuse me, that would be 62 to the 8th, I have this. So how many different passwords do I have now? Well, now it's 62 to the 5th plus 62 to the 6th plus 62 to the 7th plus this. So these possibilities plus these possibilities plus these possibilities plus these possibilities equals whatever. And once again, this is monstrous because if we look at this, 62 to the 5th is equal to 916,132,832 different possible passwords. And so obviously, this is shifting a decimal point at least once. This is shifting a decimal point at least once. This is shifting a decimal point at least once from the previous possibility. So this is just, like I said, just huge. But this combines multiplication principle with the addition principle. And many real world situations would be like that where you combine these two. And there's lots of other different things you can do that are considered combinatorics. But we'll look at those in some different videos.